Vadim Alekseev, who will speak today at our seminar on discrete subgroups of full groups of probability measure preserving equivalence relations. Thank you very much.
Thanks very much. It's great to be in Prague and talk to people here. So first of all, my talk will be about measured group theory, so actions on probability spaces. And since maybe that's a bit further away from interest of much of the audience, I encourage you to ask questions every time something is amiss, right? I mean, and I'll try to introduce the story quite slowly so that you'll hopefully understand the background. So what is yeah. So what's the story about? We are interested in discrete groups. So throughout this talk, the gamma will be a discrete, mostly countable, but this doesn't matter that much group. And measured group theory studies these objects via letting them act in a measure preserving way on a probability space. So this is a standard probability space. So I'm use a probability measure, and gamma acts in a probability measure preserving way. Acts in a probability measure preserving and this is standardly abbreviated as PMP way. And the question is, what can we learn about groups by considering these actions? That's kind of the main theme. So an example, two examples of these situations that are very classical is one, I can let Z, the group of integers with addition, act by irrational rotation on the circle. So to specify an action of Z, I just have to specify how the generator acts, and the way it acts is sending a complex number to this multiply with e to the I alpha, where alpha over pi is irrational, let's say. This need not be, but rational actions are kind of boring because they're periodic here, right? So if I want something aperiodic, then this is a nice example. So this is a rational rotation. Slightly more generally, I could do the same by taking, say, some compact group K with a Haar measure, compact group with a Haar measure, and taking any dense subgroup and letting it act by left multiplication on K with a Haar measure. This is another kind of nice example of this sort of dynamical system. Another very universal example is the Bernoulli shift, Bernoulli action. I can take 0, 1 to the gamma, equip it with a measure which is just the product measure of the standard 1/2 measure here, and let gamma act by left translations on this space. This is another probability measure preserving action, which is interesting to understand. Okay. So the actions that I've considered so far are free, or almost free, in the sense that the set of points which are stabilized by a non-trivial group element has measure 0. This need not be the case, and in fact, a particular interest in this talk will be in actions which are not free. But to understand them, let me first introduce another player here. So one very classic subject in measure group theory is if you have this action, such a PNP action, what you do is you pass to the equivalence relation generated by this action. So this is the orbit equivalence relation. What is this? These are just pairs of x comma gx, where x varies over your space and g varies over your group. This is a nice subset, nice Borel subset of x cross x in such a PMP action. This is what you study. This is what you can study if you want to understand group actions. So a surprising thing which happens here is the following. It's essentially a theorem by von Feldman and Weiss from the 80s. Namely, there are lots of groups which generate isomorphic equivalence relation here. Namely, let me write it like this: all PMP actions of Z, and more generally, of what's called amenable groups. Amenable group gamma generate, or amenable groups gamma generate the same equivalence relation. And to be really precise, I will have to say ergodic here. And ergodic means indecomposable here, so I don't have an invariant subset of measure different from 0 and 1. So ergodic is indecomposable. Generate the same equivalence relation. The equivalence relation, which is called the unique hyperfinite equivalence relation. So in view of this theorem, you have lots of ways to understand what it looks like. For instance, the action on this irrational rotation action of Z generates it. It's ergodic. The Bernoulli shift of Z and of Z square and Z to the n and every abelian, every infinite abelian group and every infinite amenable group generates the same equivalence relation. So you completely forget a lot of groups here. You just view amenability here. Yes. They are isomorphic as PMP equivalence relations. I swept under the rug the definition, but what it formally means is, so this equivalence relation, they are always on the probability space, right? So you can say that this is an equivalence relation on the standard Lebesgue space. Okay, you have to say what it means for it to be measurable, meaning that this is a Borel subset. And you have to say what it means for it to be measure preserving. And what it means to be measure preserving is if you have a subset here which projects injectively on the first and the second leg, then the measures of the images are the same. That would, the way to think about this is the typical subset of this form will be you take a subset here and you move it by a group element. And then you have this sort of subset. And then it says that the measure of the subset and the measure of its image is the same. So in the natural kind of setup of these equivalence relations, you just have this one. So for non-expert in geometric group here, I didn't define what amenable groups are, but let me just make let me not rewrite the definition, but the class of amenable groups that contain they contain all abelian groups, solvable groups, and all groups which are of sub-exponential growth, meaning that their Cayley graph don't grow exponentially, and a non-example, so non-amenable groups include free groups on at least 2 generators, and everything which contains such a non-abelian free group. For instance, SLN-Z would be a non-amenable group for n at least 2. So, and in fact, this Kohn-Feldman-Weiss theorem says a little bit more. It essentially also implies that this free group will never generate a hyperfinite relation. So in this realm, there's amenable world where everything collapses together by this theorem, and there are non-amenable worlds which are strange. And somehow, in a certain way, amenable groups could be viewed as kind of small-ish, whereas non-amenable groups are kind of big-ish. This can be justified by the fact that, well, the non-amenability of F2 is very much connected with the Banach-Tarski paradox, where you decompose something in 2 pieces. So you kind of some expansion here. Okay, so or you can say, okay, amenable groups are sub-exponential growth groups are amenable, and this grows exponentially, so it's kind of bigger than that intuitively. Okay, so all right, so that's the situation which was already observed some time ago, and an interesting another object which people study in this context are full groups. So from these 2 full groups here. So what's a full group? Suppose you have such an equivalence relation coming from a group action, then you denote it G. Then you can look at the following group. These are all the automorphisms of your probability space, which respect this orbit equivalence relation in the sense that if you look at where your point is sent, it will be always sent to some orbit equivalent point, or all or almost all x and x. Okay, so this is a formal definition. The way you should think about this is really the following kind of picture. This is your probability space. I always write my standard probability space as initial because that's the unique probability space that is out there, standard probability space that is out there. A typical element of the full group, which will have decomposed your space into countably many pieces, and on each piece it acts by some sort of group element. So it acts by G1 and sends this here, it acts here by G2 and sends it here, and it acts here by G3 and sends it somewhere else, and it kind of permutes these pieces accordingly. That makes sense so far? And it's something that is constructed piecewise out of your group action. This is a big group. So G is in fact a non-separable Polish group. So this is quite huge. Oh, sorry, sorry, non-locally compact. Sorry, sorry. Of course, it's separable. It's not locally compact. But it's a big group. And well, when I say Polish, I need to specify a metric, and here I can even write down a very nice bi-invariant metric with even a bi-invariant metric, which is the following. If I want to say how different my two elements are, I take the measure of the sets of points where they do not coincide. So a bi-invariant metric, okay, you can view this as also sort of a length function. So the distance of S to 1 in particular, this is the measure of 1 minus the measure of the fixed point set of S, or it's the same as the measure of they call the support of S. And the support of S is exactly the subset of points which are actually moved by S. Okay. So this is very natural. And you can study this Polish group from various standpoints. A very classical result is that if the R is our unique hyperfinite equivalence relation, then the full group is extremely amenable. What does this mean? This means that if X acts on some compact space continuously, then there is a fixed point. This is a situation which is really a peculiar property of these big Polish groups, that they can be extremely amenable without being very trivial. And this is an extremely strong property. You force a fixed point in every action on a compact space. This is rarely happening. So since I haven't defined amenability formally, this is really a strengthening of amenability, which only requires this for some actions on convex subset of locally convex spaces. Okay. Now, if you compare this statement that if you have a hyperfinite or amenable equivalence relation, then this guy is extremely amenable, with the fact that the free group is not amenable and therefore will never generate this hyperfinite equivalence relation in a free action, then you might wonder about the following question. Which is wide open still, but which motivated what I'll be talking about in some minutes. Namely, can you embed, so if R is the hyperfinite equivalence relation, PMP equivalence relation, can you embed F2 into the full group as a discrete subgroup? And discrete meaning, of course, in this Polish topology and in this invariant metric. So, okay. To let you appreciate this question a bit, let's make a couple of observations. So if let me maybe do it like this. If, say, lambda in G is a discrete subgroup, then just by definition, we can attach a number to it, which is the minimal distance to the identity element in this metric of every non-trivial group element. So this is the infimum over the distance of lambda to 1 in over lambda not being identity. And this is then strictly positive. So you cannot have a sequence which converges to the identity, right? Because you are discrete. And we call this, just for the purpose of this talk, the modulus of discreteness of lambda. And I'll be saying lambda is 1 discrete or 1/2 discrete if 1 or 1/2 is this modulus of discrete. Okay. So by the fact that non-amenable group a free action of a non-amenable group cannot generate a hyperfinite equivalence relation, the answer is obviously no if you want 1 discrete. So the answer is no if you want 1 discrete embedding, want F2 in G to be 1 discrete, in R to be 1 discrete. But it's open if you ask for 4/5 discrete or 99% discrete. So, and what does 1 discrete means? 1 discrete, by this definition of the distance, means that every non-trivial element has full support. So the action is free. And that's why it doesn't work. F2, if you act freely, if you have a free probability measure preserving action, then it never generates anything hyperfinite or amenable, because free F2 is non-amenable itself. That's why this doesn't work. Does that make sense so far? So, okay, so right, since a free action of F2 cannot generate the hyperfinite or amenable finite equivalence relation. But this question essentially asks, well, if you are kind of somewhat non-free, but still so that you embed injectively, maybe this works. So the answer is unknown as of now. Despite the fact that it's unknown, it motivated us together with Andreas Tom, Alessandro Carderi, and Robin Tuckerdrop to study discrete subgroups of these full groups more generally or more systematically. And for instance, asking the question, are there maximally discrete subgroups? I'll come to that a bit later. But before that, let me maybe make a slight digression and make a remark here. So I decided to talk mostly about measured preserving equivalence relations today because there somehow you have a bit more control about what is going on. But let me just mention that all these questions can very parallelly be asked in the context of operator algebras. So there is an analogy. So those questions in operator algebras, more particularly von Neumann algebras, can be understood as follows. The analog of the hyperfinite equivalence relation, so the hyperfinite equivalence relation corresponds philosophically to the what's called the unique hyperfinite 2-1 factor. So let me just say that this is still denoted by R, but there won't be any confusion. This is the infinite tensor product of 2x2 matrices as a von Neumann algebra. And in fact, you can even produce this algebra just from this unique hyperfinite equivalence relation. If you take what the groupoid algebra or the algebra of the equivalence relation, you produce this gadget. Okay. And the full group of the hyperfinite PMP equivalence relation sits naturally in the unitary group of this hyperfinite 2-1 factor. And even you can put it isometrically there because on this unitary group, since this gadget has a trace, it has a 2 norm, and you can put the distance between two unitaries to be the 2 norm of their difference. And let me think, I think if you put 1 over square root of 2 here, then that will be isometric. I mean, you have to put some constant here, which I always forget. But essentially, this this full group embeds very naturally and very nicely into the unitary group of the hyperfinite 2-1 factor. And of course, the same question for this. So like question prime, which is really just a version of this. Can you embed F2 as a subgroup of U of R discretely? Okay. And actually, I mean, despite both questions being open, I would personally believe that the answer should be simultaneously no or yes, because everything just works parallelly in this world somehow. Whatever you do with PMP equivalence relation, you can usually do with 2-1 factors. Okay. However, so in the world of 2-1 factors, you have other constructions for them. So if you start with operator algebras, then you can ask the following thing.
Sorry, Vadim, can I just
Yeah.
ask a quick question? How does the full group of the equivalence relation relate to the unitary group of R? Are they the
Oh.
same or?
No, they are not the same. They are much more in the unitary group of R. So the full group of the equivalence relation is essentially almost, I mean, it's not quite the same, but it's not so far from the normalizer of L infinity of X inside the unitary group. So the normalizer is, if you want a precise statement, the normalizer is exactly the elements of the full groups where you are also allowed to multiply with some functions with values in U1 at each stage somehow. So it's we are like that two Polish groups. It's embedded isometrically. This is far bigger, and this is a normalizer of something which relates to the action, essentially, like almost not quite the normalizer, but kind of philosophically it is. Okay, so if you start from operator algebras, then you can ask the following. So take any discrete group. You can make a von Neumann algebra out of it. Just take the left regular representation and generate the von Neumann algebra by weak closure. And the trace is also canonical. So surely gamma sits in the unitary group of L gamma as a one discrete subgroup. But you can ask, is it contained in a maximal discrete subgroup, or maybe it is maximal discrete in some cases? Again, we don't know. But the corresponding question, if you try to transport it back to the world of actions, would be the following. So we start with this probability measure preserving action. If gamma acts freely, free PMP action, then again gamma sits in the full group of the equivalence relation just because every element is acts just in one chunk, moves something as a one discrete subgroup. Is it, well, I mean, are these groups maximal discrete, or do they sit in maximal discrete subgroups? Okay. And that was basically that's something you ask yourself because if you just say discrete here, and it's maybe too difficult, you cannot answer this question. But some of these questions we can now answer. And let me then switch to the statements that we can prove. Well, I'm raising maybe that question so far. Okay. Good. Let me just present the results that we can maybe could reduce so far. To do this, I first have to introduce a property of a group which will play a role in deriving all this. And this is called the MIF property. and MIF stands for mixed identity free. Okay, let me explain to you what is going on. So gamma is a discrete subgroup. Discrete group. What's a mixed identity? Okay, so a mixed identity W in gamma free product Z is an element such that for every G in gamma, if I evaluate this word at G, then I get 1. Now, this might be slightly confusing for you because I haven't told you what it means to evaluate the word. So what's a word in a free product of gamma with Z? This is some gadget of the form, G1 to some power, then T to some power, then G2 to some power, then T to some power, etc. Right? This is what a word in such a free product is. And evaluating this word at G means replacing T by G. Okay? So this would be, by definition, for such a word, G1, K1, G, K, G alpha 1, G2, K2, G alpha 2, etc. So, right? So if I have a word, this is an expression like this. I can replace this variable T by a group element, and this is a mixed identity if it evaluates to 1 at every group element. So it's some strong form of identity that a group can satisfy. Does it make sense? Far? Let me maybe give you an example. Yes, but this is more general than laws. So in laws, you do not want constants. This is kind of a Lewis constant. Know what group laws are. So an example is if C in gamma is a central element, right? Then C commutative with T is a mixed identity. So this is CT, C inverse, T inverse is a mixed identity. Okay, because this C is just these constants here, and T is my variable. And what this says is that everything commutes with C. Does that make sense? Okay. Okay. All right. Now I can define what a MIF group is. A MIF group is a group which doesn't have any non-trivial mixed identity. Group gamma is MIF. If there is no non-trivial mixed identity for gamma. Okay. This is a interesting class of groups which people in geometric group theory have been studying in recent years. So of course, there's kind of a trivial example that non-abelian free groups are MIF. This is, I would even argue this is pretty easy. Slightly less obvious thing is that ESL and Z for n big or equal to are MIF. And even less obvious is the following. So if you remember this, what I told you about amenable group. So there are like abelian groups would not be MIF because they have centers. Solvable groups, again, for important groups and solvable groups would not, generally speaking, be MIF because, of course, solvability just means that you have some identities. Subgroup measure graphs is different, but it's actually quite a non-trivial business to construct an amenable MIF group, but that can be done. So there is an example of Hall and Olsen. There exists an infinite amenable, I mean, infinite is automatic amenable MIF group. If you are finite, then surely you satisfy an identity, satisfy a mixed identity by using two-weighted commutators. So, okay. No, it wouldn't be elementary. I mean, the example is not elementary. I'm actually, let me think. I don't think it's known that elementary amenable groups are not MIF. So I mean, but it's difficult to deduce such properties. So they had constructed it in some very specific way. Yeah, I mean, there are more examples there, like cylindrically hyperbolic groups, which generalize with free groups vastly. They can also be proven to be MIF with certain restrictions on the amenable radical. And there are also some other kind of lattices and Lie groups type of result, which we don't need here. So there's more to that. But for us, I think this third point will be important. Okay. Now, okay, so I'm an ability. Oh, here. Oh. All right. To formulate our results, I will also need some properties of the actions. So if, let's say, gamma acting on X mu is a PMP ergodic action, so ergodic means just indecomposable, as I mentioned, then there are some strengthenings to ergodicity, which might be useful to consider. So there are some strengthenings, useful strengthenings of ergodicity, namely the action might be mixing or weakly mixing. So the action might be mixing weakly mixing. And let me just let me just say that a typical example of a mixing action is the Bernoulli action. And I don't really have time to write down the proper definitions here. The the way to think about mixing is the following. If you take two subsets and shift one of the subsets by your action, then they become almost independent as events in your probability space. For Bernoulli, take just a finite window. If you shift it from itself independently, that will be independent event. That's why they're mixing. And well, the opposite somehow philosophically are compact actions. What does this mean? This means, per definition, that the closure of gamma in the Polish group of automorphisms of your probability space is compact. But this is, of course, a definition which doesn't explain much. But the examples that I was, the example of a dense subgroup in a compact group, so this compact with a Haar measure is an example of a compact action, and that's where they get these notions. And these are the opposite of mixing. For our purposes, will be enough to just have these classes. Okay. Now I've set up the scene to tell you about theorems. Good proof. So there will be several of them, and I personally consider it as a slight drawback that we don't have one theorem from which all of these follows. But okay, I mean, that's sometimes how it works. So what are the results? Theorems of myself, Alessandro Carderi, Tom, and Robin Tucker-Drob. Okay, so if gamma acts faithfully on a probability space, so PMP action is a faithful PMP action. And let gamma be a faithful PMP action. And suppose at least one of the following is true. Well, the first variant would be that gamma is MIF, the action is weakly mixing, and essentially free. Or you can suppose something slightly easier to digest. Gamma is torsion free, and the action is mixing. Then, if G is an element in the full group such that the measure of the support of G is less than 1/3, then the group generated by gamma and this one element of the full group is not discrete. In particular, gamma is contained in a maximal discrete subgroup. So, okay, while I'm raising this thing, let me explain the in particular part. Of course, this in particular follows from this because if you add elements, then this condition tells you that you have to stop at a certain elements with small supports. You cannot get below 1/3 in the measure of the support. Otherwise, you collapse to something non-discrete. And so by some Zorn-Lemma argument, you're contained in a maximal discrete subgroup because you never drop below 1/3. However, so this is kind of an abstract statement in some way, in the sense that we unfortunately do not yet have any example where gamma would itself be maximally discrete. So these maximal discrete subgroups in which we are contained and in a Bernoulli action are pretty mysterious so far. Okay, so this is one theorem. Then there are some counterparts to it which look similar, but they're kind of formally different, and they require even separate proofs for interesting reasons. So if gamma is MIF and gamma, and this is just a PMP ergodic action, but now I don't assume that this is free. So here I assume that the action was free for the first part. Action. Then if gamma in this full group is discrete, then it's 1/2 discrete. And you might see, okay, I mean, this is something very similar here, but there I was assuming that gamma is MIF, and then I was deducing something about this group. And here we don't know whether this is MIF or not. Whereas here I'm supposing that the acting group is MIF, and then it is discrete, even if it has some fixed point. So it's very similar, but formally different, and the proofs are independent somehow. Okay, and the third theorem is if gamma is MIF and the action is again faithful, let's say faithful as well. It's faithful, P, faithful, and compact, then it's even better. If it's discrete, then it's one discrete. So for compact actions, essentially you deduce that the action is free. Okay, so compact actions are somehow better in this regard. Okay. And of course, this begs the question, which we cannot yet answer, is can you remove compact here? Of course, if you could, then the answer to the question about embedding F2 discretely into the full group of the hyperfinite relation would have the negative answer, because then it would imply by the fact that it's, if it would it would imply that it's one discrete automatically. Okay, so in the remaining 5 minutes, let me tell you about the main device that lets these theorems work. The main device is what we called commutator contractivity. And this starts with a very elementary observation, which is actually I think have been observed first in just finite permutation groups, and has even used them. They recently learned. So the technical idea, what's called commutator contractivity, at least for us. And the this hinges on the following lemma. If gamma acts just on some set X, just a set, and and the support of an element is the set of points which is moved as usual. Let G and H be in gamma and denote by A, G, comma, H the support of G intersected with the support of H. Then the support of the commutator is contained in the union of this intersection and this intersection shifted by both group elements. So observe that G times this intersection of supports is the support of G intersected with the support of the conjugate. Because G times support of H is the support of the conjugate of H by G. And this is why the support of the commutator, so the commutator consists of GH, G inverse, H inverse. So this is G times the conjugate. So it's no wonder that something like that is going on. Now, why is this useful? If we have now a probability measure preserving action, right? If gamma acts on X mu in a PMP way, then what does this mean? This implies that the measure of the support of the commutator is less or equal than 3 times the measure of the support of G intersected with the support of H, because the measures of all these sets are the same, right? And this 3 is exactly the reason for this 1/3. So let me just briefly, because time is running, explain what's going on technically. So if you want to prove a statement like this, you start with your element of the full group, which has small support, okay? And what you do is you take a commutator with of G with a group element H, which is from your original acting group. And then what you would like to have is that the support of this commutator is like uniformly smaller than the support of G was, okay? Because then if you have this mechanism, then you take this commutator, it shrinks the support, so it's closer to the identity. Then you take, if the mechanism works, you take another commutator, it shrinks the support even more. And then by iterating the commutators, you get a sequence of elements which converges to 1. And that's why the group is not discrete. Now, why? Now, what's the kind of next idea to really have this working is what you would expect in the best possible situations is that, well, is that these supports should be independent. Because if these supports are independent, then here you have the mu of the support of G squared. And then by just a very elementary estimate, the support really shrinks. And to make this independent, this is where you need some mixing conditions. Okay? I mean, having independent supports, having something independent stems from mixing. Finally, where do you need MIF? And this is what, say, in point 1 was important. What can happen? So the idea of the proof is you take iterated commutators. But what can happen a priori is you take this long, strange iterated commutator. It has small support, but maybe it's just equal to the identity. Maybe it collapsed all the way down to the identity element. And you want to prevent this. You want that this is a non-trivial element. And how do you prevent that something collapses to the identity, you say that, okay, I mean, if this commutator collapses to the identity, this is sort of an identity in your group if this happens for all group elements. If you cannot find the elements here which would make this work, and that's where the MIF condition enters. So this mixed identity free is needed so that this iterated commutator construction works but does not collapse all the way to the identity. And let me stop here. Thank you.
Thanks very much for the nice talk. Do we have any questions in the audience? Dennis.
Yes. If you have finite conjugacy class, for instance, like it should be ICC, because if you have a finite conjugacy class, right, you have a group element C now that GCG inverse equals to like C1 up to Cn, right? So GCG inverse times C1 inverse is 1, or say GCG inverse times C2 is 1, right? Or C to the n, and then you take the iterated commutations of all these gadgets so that if at least one is 1, then everything collapses, and this is a mixed identity. So. I would expect this to work out in some ways. The problem is that in the applications we had in mind, it's already kind of, I mean, already having this mixing of the independence for this two intersections is some sort of a mixing condition which is non-trivial to have, so you have to impose it essentially in the theorem. And if you want some estimates on higher intersections, that this is sort of a higher order mixing, which is even a subtler thing in ergodic theory. So we didn't really look into that because that was difficult enough for us. But probably it can be done. I mean, you can define what higher order mixing is, but I think it's, if I give you just a dynamical system and ask whether this is, higher order mixing, this is much more subtle question than to decide whether it's compact, ergodic, or weakly mixing, because here you can use some representations here in Hilbert spaces and kind of Koopman type of ideas to deduce this, where higher order mixing is like, to me, it's pretty complicated as in producing it. MF, I mean, that's true that in fact what we care about are only mixed identities in this form, but in many examples where you try to understand which mixed identities the group have, the commutators are actually the problem that you have to study. So somehow, mixed identities which are unbalanced, for instance, in T, at least if your group acts somewhere in a nice way, they're usually easy to handle that they're not mixed identities. So in some sense, I mean, I'm not saying that there is a formal statement, but from the techniques that people use when analyzing mixed identities, the commutators are actually one of the bad situation, or like the balanced words bad, if you can reduce the commutator somewhat. Yes. In fact, I mean, I didn't have time to mention this, although I kind of point it a bit. There is a counterpart to this theorem for group von Neumann algebras. So you can also prove that if gamma is MIF, then gamma is contained in a maximal discrete subgroup in U of L gamma. So you replace the full group with U of L gamma. It also works, and the way it works is because MIF. Let me think a bit. Yes. Right. So the MIF condition is equivalent to the following. If you take the ultra product of gamma, then MIF is the same for a countable group as to having an element here, which is independent, which is free from the diagonal copy of gamma there. So this is what's called an asymptotically free sequence. And this is how you can also produce some argument like this in the group von Neumann algebra case. But if you want to have a kind of a global condition, then with ultra product, then that's it. We don't know. I mean, in some sense, we were much more interested in the opposite, namely in this maximal discrete subgroups, the subgroup that you get abstractly from this result in which it is contained. But unfortunately, as I said, unfortunately, I cannot give you a copy of an explicit copy of a maximal discrete subgroup. By Hull and Ossin, however, they even exist in the amenable hyperfinite relation because you have an amenable MIF group, and to that this theorem applies. So it sits in some maximal discrete subgroup in the hyperfinite one factorial relation.
Of course, one could consider topological full groups from topological dynamics instead. Now there's no hyperfinite equivalent, but maybe one could look at like the AF equivalence relation related to the 2 odometer or something that would give you M to infinity.
Yes. Well, I think in kind of conceptually, there is the following problem. If you like this metric here is really about measure, right? So if you just look at the topological full group, it's usually countable. It's countable, right? So it's another situation where you don't really get this kind of these Polish groups into which things embed. And then essentially, I don't know how to properly formulate the question about maximal discrete subgroups there, because the topological full group itself is countable. But maybe again, as we discussed, maybe if you close it off in some way or something, you might start to do something, but I'm just not aware of topological dynamics that much as to be able to do it.
Any other questions? Not, let's thank Vadim again. And I'll just briefly announce next week's talk. We have Tomasz Brzezinski coming from Swansea and Białystok, who will talk about Lie brackets on affine spaces.